Chapter 10 is about roots and radicals. Roots and radicals. The roots and radicals that you're probably already very familiar with are square roots. All right, we start with a problem that says find the square root, and it gives you a particular number. It puts it inside what's called a radical sign, and it asks you to find the square root of 169. It is equal to whatever number it would take to square to get 169. Okay, so your calculators, your scientific calculators should have a square root key. Or you may know this one off the top of your head. What is the square root of 169? It is 13. Now, in your answer choices, it says select the correct choice below. If necessary, fill in the answer box with your choice. Okay, we would have chosen A, and it says the square root is, and you would have typed in the 13. When would you have chosen the square root is not a real number? What if you had been given the problem, what is the square root of negative 25? Well, what's the square root of 25? 5. Okay, because 5 squared is 25. What can you square and get a negative answer? Well, the answer is imaginary numbers, but we haven't even talked about those yet. So this one would be not real. You cannot take the square root of a negative number, because when you square a number, a negative times a negative is positive, a positive times a positive is a positive. You can't get an answer whose square is negative. So that's the kind of problem that would be not real. All right, problem number 2. It asks you to simplify the square root of 1 over 81. If you're asked to simplify the square root of a fraction, just look at the numerator and look at the denominator. This is the same as the square root of 1 over the square root of 81. 1 is a perfect square. What's the square root of 1? 1. 81 is a perfect square. What's the square root of 81? 9. So the answer to this is 1/9. And if you checked it, 1/9 times 1/9 would give you 1 over 81. So I would once again choose A. I would put in the fraction 1/9, and the root is not a real number. That would have been the answer if the radicand, and that's the name for the inside of the radical, if the radicand had been negative. So it could be helpful to you to know perfect squares. So we're going to make a little list of perfect squares over here. Yes, there is. There is a sheet under handouts, and what it does is it gives you 6 copies of it. And I have some of those in my office, and I can bring them back. I can scurry down there at the end of class and get those. It is available under handouts. I think it's called the Power List. But 1 squared is 1, 2 squared is 4, 3 squared is 9. You could, of course, create your own list. 4 squared is 16, 5 squared, 25. In my 307 class, we created this list and we talked about it when we were factoring the difference of squares so that we would recognize perfect squares. 6 squared, 36, 7 squared, 49, 8 squared, 64, 9 squared, 81, 10 squared, 100, 11 squared, 121, 12 squared, 144, and so on. And I'm actually off the screen here in the classroom. The list has it to 20 or not?
Yeah, 20. It goes to the fifth power too.
Oh, okay. So the power list, if you decide to print it off, and you do get 6 little blocks that are repeats of it, it has the numbers 1 through 20, and it has them squared, raised to the third power, raised to the fourth power, raised to the fifth power. So it's kind of a nice little handout. All right, so it's nice to be able to recognize perfect squares. Now we need to be able to simplify radicals, square roots, where there are variables inside. Now this problem asks us to simplify x to the 12th power, the square root of x to the 12th power. Well, ask yourself, what could you multiply times itself to get x to the 12th? X to the 6th. And you could check it. X to the 6th squared. Do you remember what the power rule says? The power rule says when you have a base to a power, raised to a power, you multiply. So that's x to the 12th. So that would be a check. Keeping this in mind, what did a square root do to the exponent of the variable? It cut it in half, didn't it? Okay, so that's what a square root radical does to an exponent, which might make you wonder, what do I do if it's not even? And that'll come up in just a minute. Let's look at problem number 4. It says simplify by factoring, assume all expressions under the radical represent non-negative numbers. The reason they have that full instruction is that, remember, you can't take the square root of a negative number. So if it's a variable, they're just saying, don't worry about it, the variable's not negative. All right, wants to know what is the square root of 16 times x to the 6th. Okay, what's the square root of the 6th? 4x to the third power. You take the square root of numbers, coefficients, the way you always have. You take the square root of variables with exponents by taking half of their exponent. Now, not all numbers that you're asked to work with are perfect squares. Number 5 says find the square root, and it says, what's the square root of 13? All right, 13 is not a perfect square. And I'm looking at the instructions, and it says not enough. I think it might say more online because I would need to know the number of decimal places. And I believe that when you're looking at this screen online, that it does tell you the number of decimal places because it would certainly have to. So that's kind of a little problem for me. What if I say 3 places? And I'm really sorry because it should be saying that on the screen. The square root of 13, and let's round our answer to 3 places. So depending on your calculator, some calculators you put in the square root symbol and then the number, and some calculators you put in the number and then hit the square root button. Depends on the calculator. But I get as an answer 3.60555, and it just keeps on going, different numbers. So if it said 3 places, here's my third place, what would the 5 tell me to do? Round it up, and this would be approximately 3.606. Okay, so I'm sorry, there seems to be a little piece of the directions missing. So if it is not a perfect square, then we will use our calculators, unless it just says to simplify, which is coming up. Well, and see, here's number 6, and it says it better. Let me go back up here. Yeah, all right. Problem number 6. This one does say approximate the square root to 3 decimal places. Make sure you know how to use your calculator to get a square root. And if you don't, I'll be glad to work with you. We can either pause this recording and I can work with you individually, or you can wait till the end of class and I can show you how to do it. It's up to you. All right, on my calculator, when I ask it for the square root of 41, if I round to 3 places, I'm going to get 6.403. Is that what y'all got? Okay. So square roots, if they're perfect squares, hopefully you'll recognize them. If not, your calculator will recognize them. Non-perfect squares, you put in your calculator and you'll have rounded it to some particular place value. Question number 7 switches gears a little bit, and it asks us to find a root, but the problem is the cube root of 8. Now, when there is a tiny number written right there, it's called the index. If you're dealing with square root, then the index is a 2, but it's implied. They won't actually write it. This means, what number do you have to cube to get 8? And the answer is 2. And it is because, although you don't have to certainly answer because, 2 to the 3rd power is 8. So a cube root, you're asking yourself, what do you have to cube to get that number? Your calculators probably have a cube root function on them. With the TI graphing series, the 82, the 83, the 85, whatever, it is under the math key. Under the math key, I think it might even be choice 4 is a cube root. You would do that first, and then you would type in the number and close the parentheses and hit enter. All right, number 8. It says to simplify, and it has the cube root of x to the 12th. Now, I know how to take the square root of x to the 12th. I took half of the exponent. What do you think you'll do to take the cube root of x to the 12th? Not by 2, but by, you will divide the index into the exponent. So that'll give me x to the 4th. You might wonder, well, what would I do if it's not divisible by 3? And we really won't do a whole lot with that, but it'll be similar to what I do with things that are, I ask you to take square roots, but it's not even. There is a mechanism for simplifying it, if not getting a nice, perfect answer. So, when you're asked to take a root of a variable with an exponent, if you can divide the index into the exponent, then you do. And if you can't, for right now we don't know what to do, but shortly we will know. All right, number 9. It wants us to find the cube root of negative 64x to the 6th. Okay. Now, if it were a square root, our answer would be this is not real. Square root. But can you cube a number and get a negative? Yeah. Yes, as long as you're cubing a negative number. So the cube root of a negative is negative. So what is the cube root of 64? It will be a negative 4, and then x to the 2nd, because you divide the index into the exponent. So you can take cube roots of negative numbers, but you cannot take square roots of negative numbers. And I could generalize that. You can take, in fact, I'm going to generalize it down here. If I ask you to take an even root of a negative number, that is not real. If I ask you to take an odd root of a negative number, it exists as a real number. So you can't take even roots of negatives, but you can take odd roots of negatives. All right, number 10 is sitting up here. This is 10. Its problem number is not showing in class. There it is. It says simplify. If an expression does not represent a real number, state so. And we state so. You type a capital N if the root is not real. Okay, this is the fourth root of -1. All right, that is an even power of a negative radicand, and so this is not real. By the time we get to problems 43, 44, around in there, we will have a non-real answer for the computer. But for right now, we're not supposed to do that. So if you already know, put it on the back burner. You're just supposed to say it's not real right now. Okay, keep on going. We won't have one of these on our test. It says find the root, assume that the variable represents non-negatives. Okay, it is a fifth root. Fifth root of 32x to the 15th. What in the world could you raise to the fifth power and get 32? 2. And you might have to do a guess and check on that. You might say, well, I don't know. And so you start playing with some numbers. On the TI series calculators, there is an nth root function. You can type in a 5 because it was fifth root, and then go to math, and I think it's maybe choice 5, and hit, choose the 5, and then type in the 32. So you have to tell it the index first on that. Or you can just guess and check. All right, this is 2, but we're not through with the problem, even though I digressed. What will I do to find the fifth root of x to the 15th? I'll divide, and I'll get x to the third. So make sure that you divide the index into the exponent. Is that okay? So, of course, it was this choice, and it was 2x to the third. Number 12. I'm going to scoot down to the bottom of this particular page and write down a couple of notes. Okay, if I have the square root, let's say x, that is the same as x to the 1/2 power. We have not, at least in our classes, had fractional exponents before. But a fractional exponent represents a radical. The denominator of the fractional exponent is the index of the radical. So if I said, what's the cube root of x? That would be x to the 1/3. Now, if I have, say, the fifth root of x to the 4th, if there is a power inside and an index outside, then that's what makes up the fraction. It is x to the 4/5. Just so you won't ever forget, the index is the denominator. There is probably written in your textbook something that says if you have the nth root of x, that is x to the 1/n. If you have the b root of x to the a, that is x to the a/b. So radicals turn into fractional exponents back and forth. You would find, if you took a calculus class, that it's very, very helpful to have this fractional exponent notation available to you. You won't find it that big a deal in here, but you would find it very, very useful in calculus. All right, if we back up to problem number 12, it says evaluate 16 to the 1/2 power. Now, although you are welcome to think about it in that notation, I personally typically think about it in radical notation because I just think about radicals. Okay, that translates into the square root of 16. The exponent on the 16 is the implied 1. The index is the implied 2 of the fraction. So what is the square root of 16? 4. So that answer is 4. Number 13 changes the instructions a little bit, but I'm going to do exactly the same thing. Number 13 says use radical notation to rewrite 81 to the 1/2 power and then simplify if possible. Well, what root am I taking if it's to the 1/2 power? Square root. So this is doing what it said, rewrite it in radical notation. Now, what is the square root of 81? It's 9. That's the simplifying process. My math lab really does not know if you ever did this. I do it, but it doesn't really know, even though it tells you to do that. Number 14. It says use radical notation to write the expression, simplify if possible. So I have the square root of, now how do I know it's a square root? Because it's 3/2. And so the denominator 2 becomes the index. We don't write it. I have 4 over 81, and there's a 3. Now, let me show you. You can put the 3 inside, or square root 4 over 81. You can put the 3 on the outside. Now, if you look at those two expressions, what I'm saying is the fractional exponent, 3/2, does two things to the base. It takes the square root because of the denominator. It raises it to the 3rd power because of the numerator. The order that you do those is up to you. The first way I wrote it would say cube this and then take the square root. The second way I wrote it says take the square root and then cube it. And it's totally up to you. Now, my preference is the second way. Why do you think that the second way would be my preference? Can you take the square root of 4 over 81? Do you know the square root of 4? Do you know the square root of 81? 9. 2 over 9. Then could you cube 2 over 9? Well, I think you could. You might need a calculator help, but let's look at it. If I did it this way, that is 2/9 cubed, which means 2 cubed over 9 cubed. 2 times 2 times 2, 8. 9 times 9 is 81 times 9 again is how much? 729. Now, the reason I like to do that is that by taking the square root, I get smaller numbers to work with, and then I cube them and it's not so bad. Whereas if I did it the other way, I'm going to cube these numbers. Now 4 cubed, well, that's 64. 81 cubed, that's jumbo. Okay, so this way I'm going to end up trying to find the square root of 64 over, I have to use my calculator, Oh, okay. 531,441. Okay, big numbers. Now I have to take the square root of that. Now, the square root of 64 is 8, and the square root of this 531,441, I don't know, so I'd have to do it on my calculator. And of course, I get the same answer of 729. So, if you take the root first and then raise to the power, you're dealing with smaller numbers getting the same answer. If you do the power first and then take the root, it's just a whole lot bigger. Does that make sense? So, if we get the same answer, my preference is this way. Root first, power second. Oops. All right. Is everybody sort of okay with square roots, cube roots, with variables and exponents and so on? Because now we're about to touch on how do we simplify a radical that's not perfect? It says simplify the square root of 75. Square root of 75. 75 is not a perfect square. I do not want to use a decimal. If you could read the instructions that are off the screen right now, there they are, type an exact answer. Doesn't want a decimal approximation. This is the process called simplifying radicals. With everybody having really powerful calculators nowadays, I question how completely valuable this is anymore. This was very valuable before everybody had a calculator. Now it's marginally valuable, but we still teach the process. Here's what we do. We factor it. To factor means to find things that multiply together to give you 75. Okay, now there's a lot of choices. The only choice that is of value to you is one where there's a perfect square as one of the factors. So, think about perfect squares. 1, 4, 9, 16, 25. Think about the perfect squares. Can you think of a perfect square that is a factor of 75? 25. It is 25 times 3. Does everybody agree 75 is the same as 25 times 3? By factoring it so that you have one of the two factors as a perfect square, you can do this process called simplifying. What is the square root of 25? It is 5. It is rational 5. That's not under the radical anymore. Plain old 5. And I don't know what the square root of 3 is. That is my answer. 5 times the square root of 3. That's considered simplified. 5 times the square root of 3. Sometimes.
You just sit next to it like that implies
Yes,
multiplication.
it implies multiplication. Yes, it does. So whatever the radicand, which is the name of the number under the radical, the radicand, you are looking for a perfect square that goes into it. You're looking for the largest perfect square that goes into it so that you simplify it. Kind of a silly analogy, very silly, but might help you remember. When you're simplifying radicals, think of the radical sign like a prison cell. The number gets to come out, it's paroled, if it's perfect. Only perfect behavior gets you out of prison. And when you come out of prison, they give you back your old clothes and you don't look the same anymore. So, if I ask you to take the square root of 16, it's perfect. So it comes out, but it comes out as a 4. If I ask you to take the square root of 75, you say, wait a minute, that's not perfect. Let me divide it into perfect and non-perfect, and only parole the part that's perfect. And when it comes out, it becomes its rational number. So I know it's kind of silly, but might remember. All right, number 16. You are asked to simplify 5 times the square root of 75. The 5 that's in front of that is just going to tag along. Okay, so this is 5. He's just hanging on. Square root, square root. So I'm about to simplify with your help. All right, 75. We've worked with it before. What's the perfect square that goes into 75? 25. So it's 25 again times 3. I'm going to write right through the directions. That means I have 5 times, what is the square root of 25? 5 times the square root of 3, which gives me what? 25 times the square root of 3. Now that is read 25 times the square root of 3. Sometimes you will find an older math teacher who will say 25 onto the square root of 3. They'll use the phrase onto. It's not even a math phrase. But I can remember hearing it, and I've heard some of my colleagues say it once in a while, maybe some that have already retired, but just in case you ever heard that expression. Sometimes you'll hear 25 square roots of 3. Yes, and that's appropriate. I always say times. All right. Let's look at simplifying a few more. And when it says use the product rule, it's really saying break it into a product, do the factoring. So I want to simplify the square root of 28. Well, let me rewrite that so everybody in the classroom can see it. The square root of 28. I want to separate it into 2 radicals, and I would very much like the first one to be a perfect square. 4 times 7 gives me 28, and 4 is a perfect square. Okay, so it meets all the criteria. What is the square root of 4? It is rational 2, and I don't know what the square root of 7 is, so my answer is 2 times the square root of 7. And so make sure that when you're doing this in my math lab that you use the little radical sign that is in the toolbar. All right, number 18. It says to simplify the square root of 81x to the 4th. All right, now I break it into 2 radicals only if it's not already a perfect square. Is 81 a perfect square factor? Is x to the 4th a perfect square factor? Okay, what's the square root of 81? What's the square root of x to the 4th? X to the 2nd. So that one I've known how to do since about problem number 3. I would like to do number 20 before I do number 19. As a matter of fact, I kind of wish 19 weren't in there, but it's really too late, so I will show you how to do it. We're going to come back to it. It is simplifying a 5th root with exponents that are not divisible by 5. So I will show you how to do it. It won't be represented on your test. All right, number 20. It says simplify y to the 11th. Y'all remind me to come back to 19, please. Okay. Does the implied index of 2 go into 11 evenly? No. Well, I'm about to use the product rule for exponents because I want to break this into factors, powers of y, and when you multiply y to a power times y to a power, What do you do with the exponents? You add them. When you multiply, you add the exponents. So I need to break this into y, and the numbers need to add up to 11. They need to add up to 11. I want the perfect square to be as big as it can be. So how many factors of y should I include in the first radical? This number in here plus this number in the back have to add up to be 11. I want the biggest number possible. I want 10. And that means how many are going to be in the back radical? 1. Do you agree that 10 plus 1 equals 11? And is 10 the largest whole number that I can get out of 11? Yes. Now, what is the square root of y to the 10th? Y to the 5th. Because you take half the exponent, and the square root of y to the 1st, I would not write the 1. It's implied. That's how you simplify a radical when you have a variable and an exponent that's not even. Let's practice some more of that. Let's look at 21. It asks me to simplify 64 x to the 10th, y to the 7th. When I have a problem like this, I'm thinking, well, let me see if it's all a perfect square. Is 64 a perfect square? Yes. Is x to the 10th a perfect square? Is y to the 7th? No. So here's what I'm going to do. I'm going to break it. Everything that's perfect goes in the front. Everything that's not perfect falls to the back. 64, perfect. X to the 10th, perfect. Y to the 7th is not perfect. How many of those y factors can I keep in the front one? 6. Which means I have 1 to go in at the back. Is everybody catching on to how to simplify? When the exponent is not even, take 1 away from an odd number and it is even. All right, so now the square root of the perfect square. Square root of 64 is 8. X to the y to the 3rd. And then I don't know what to do with the square root of y, so I'll leave it. So it is 8 x to the 5th, y to the 3rd, times the square root of y.
Just 8. Just 8 and the exponent by itself, right?
Mm-hmm. Is that okay? Let's practice. I know I still have 19 to go back to. I'm going to make up a few problems for us to practice simplifying. What if I ask you to simplify the square root of 40x to the 13th? No perfect squares up there, which tells me I need the perfect radical and the non-perfect radical. The number 40. Can you think of, and it is almost a guess and check, can you think of a perfect square that goes into 40? Okay, 8's not a perfect square. It goes in, but it's not perfect. 6 doesn't go in, and it's not perfect anyway. Just thinking about the 40. 4. 4 goes into 40, and 4 is a perfect square, and it's the largest perfect square that goes in there. 40 is 4 times 10. And the more you work with these numbers, then the quicker your recall will be on what the perfect square is. And that's why I want to do a few extra problems. All right, x to the 13th, not a perfect square. What's the largest perfect square factor? X to the 12th, which means that the single x is back there. Now, I know that those are good factors because if I multiply them, 4 times 10 is 40, x to the 12th times x to the implied first is x to the 13th. So now, what's the square root of the perfect square? 2x to the 6th times the square root of 10x. All right, let's look at another one. What about the square root of 16, x to the 8th, y to the 5th, z to the 17th? All right. This time, the number itself is a perfect square, 16. X to the 8th, is that a perfect square? Yes, because it has an even exponent. Y to the 5th, is that a perfect square? No. How many factors of y can I keep? 4, which means I send one y back here to the non-perfect radical. Z to the 17th, no, I need to keep 16 of them up here, which sends 1 back here. Now I take the square root of the perfect radical. That gives me 4, x to the 4th, y to the 2nd, z to the 8th. And you have to be careful. 16 is a perfect square, but it's an exponent, so I'm only taking half of it, times the square root of yz. All right, let's do one more. What if I ask you to simplify the square root of 80x to the 25th power? I need the largest perfect square that goes into 80. Okay, 5 goes in, but 5's not a perfect square. How many times were you sending it in there?
16.
5 actually goes in there 16 times. So you had half of the right answer. Okay, the largest perfect square that goes into 80 is 16. Now, how are you ever going to figure out what it is? You're going to either create or look at the list of perfect squares and say, does this go into it? Does this go into it? Does this go into it? And you want the biggest one, because 4 does go into it, but it's not the largest. I'll do it with 4 in a minute and show you what that would look like. All right, this is perfect square, non-perfect square. This is 16 times 5. What about the x's? Okay, because it's odd, it's not a perfect square. X to the 24th makes that a perfect square with a single x back here. Now let's take the square root. The square root of 16 is 4. X to the 12th times the square root of 5x. Now, I want to show you what would have happened if you had chosen 4. If you said, well, I was thinking it was 4. So 4 goes in there 20 times. And then we'll do the variables right. X to the 24th and x. So that would give me 2x to the 12th times the square root of 20x, which is not a finished answer. Is there a perfect square that goes into 20? Isn't it 4 times 5? So I have to keep this 2x to the 12th and do it again. Here's going to be a 4, and here's going to be the 5 and the x. That's going to give me 2x to the 12th times square root of 4 is 2 times the square root of 5x. And if I multiply all this together, 2 times 2 gives me 4x to the 12th square root of 5x. Did I get the same answer? And I did. It's like reducing a fraction, but you didn't get the greatest common factor the first time and you had to whittle it down. So it is best if you get the greatest perfect square factor. So over here we got a 16. On the right side we got a 4 2 times. 4 times 4 is 16. Okay. Now I need to go back up to 19. It wants me to simplify the 5th root of x to the 10th, y to the 9th. You will not be tested on a question like this. All right. Is x to the 10th, well, does x to the 10th have a perfect 5th root? Yes, because 5 divides into 10 evenly. Does y to the 9th have a perfect 5th root? No. That means that I'm going to need to factor this. I have to try to remember to write down my index both times. X to the 10th stays up here. Now, y to the 9th. I need to keep the number of factors of y so that it's divisible by 5. So if I start chopping it down, y to the 9th is not. Is y to the 8th, y to the 7th, y to the 6th, y to the 5th. Y to the 5th can stay up there, which sends how many leftovers? Y to the 4th. Because 5 plus 4 is 9. Now, what is the square root? I'm sorry, bad question. What is the 5th root of x to the 10th, y to the 5th? X squared y times the 5th root of y to the 4th. The exponents have to be divisible by the index. You need to take as many factors away as needed so that you're left with a number divisible by the index. Okay? Number 22 and 23 ask us to either add or subtract radicals. In order to add or subtract radicals, you have to have what are known as like radicals. When you have like radicals, it's like having x's. If you had 5x plus 3x, you could add them together. 5 plus 3 gives you 8 x's. You can do that with radicals as long as the radicands are the same. So what I'm going to need to do is get myself a little space to work on this problem. Let's suppose I have the square root of 108 minus the square root of 75. In its original form, they are not alike. So I can't do anything. So what I'll do is think about simplifying these radicals, and perhaps in their simplified form, they might be like radicals. So I'm going to leave a little space to write some more there. And I'm going to take the square root of 108. This is my work. Can you think of, and it may take us a few minutes, think of a perfect square factor that goes into 108. And you can play with your calculator. Try dividing it by some perfect squares. 36 and 3. 36 and 3. Now we're all pretty impressed because we didn't usually start with 36. But you may have to play with the numbers. If you played with 4 goes into it, and 4 goes in there 27 times. So let me just take a little sidestep here. You have 108. If you tested it and said it's 4 times 27, that's real nice, but does 27 have a perfect square? Isn't it 9 times 3? So perfect square, something you might not have realized is that when you multiply perfect squares, you get a perfect square. What's 4 times 9? 36. So it's 36 times 3. So sometimes playing with all the factors helps a little bit. All right, what is the square root of 36? It is 6 times the square root of 3. All right, I have simplified the first radical. This is 6 times the square root of 3. Next part of my work is to simplify the square root of 75. Whoops. Oh, I messed up. There it is. Sorry. How can I simplify the square root of 75? 25 and 3. And the square root of 25 is 5 times the square root of 3. Well, this problem was rigged a little bit. The first radical was 6 times the square root of 3, and I'm supposed to subtract 5 times the square root of 3. Now, they are alike. And if I have 6 of these things and I subtract 5 of these things, how many do I get? I get 1 times the square root of 3, which we would write as simply the square root of 3. I took the 6, whoops. I took the 6 and I subtracted 5 from it. And 6 minus 5 gave me 1. I had 108 turned into 6 times the square root of 3. 75 turned into 5 times the square root of 3. Because they're like radicals now, both square roots of 3, I do the arithmetic with their coefficients. 6 minus 5 gave me 1. I don't leave a 1 written. So my answer is simply the square root of 3. All right, let's do another addition or subtraction. I have 5 times the square root of 27 minus 2 times the square root of 18 plus the square root of 12. Yes, this is problem 23. These are not like radicals. The radicands are 27, 18, and 12. So I can't do any addition or subtraction until they're alike. So can you simplify 27? Can you think of a perfect square that goes into 27? 9. So I'm going to keep the 5. The square root of 27, 9 times 3. What is the square root of 9? 3. So it's 5 times 3 times the square root of 3, or finally I can say it is 15 times the square root of 3. Second radical, I'm going to keep the minus 2, the square root of 18. It's 9 times 2. So it's negative 2 times the square root of 9 times the square root of 2. So that's negative 2 times the square root of 9 is 3 times the square root of 2, which ends up being minus 6 square root of 2. Those are not like radicals. Okay, I won't be able to add those together, but let's go on with the next part. Square root of 12. What's a perfect square that goes into 12? 4. It's 4 times 3. So that's 4 times 3. The square root of 4 is 2 times the square root of 3. So that's plus 2 times the square root of 3. I'm supposed to add up whatever I can add up. Are any of those like radicals? Yes. I have 15 square roots of 3 and 2 square roots of 3, using the language that you mentioned earlier. So if I'm going to, add those up, what will I get as the coefficient of the square root of 3? Right. I will get 17 times the square root of 3 minus 6, times the square root of 2. And I did not have very much room. You combine the like radicals by combining their coefficients and then just tack the other one on there. I left out problems on multiplication. That was very bad of me. All right, I'll talk about the multiplication as we go on, and I'll make up a few. All right, we are on problem 24. Problem 24 says to rationalize the denominator. Make a rational number out of the denominator. This is also a division problem. You will never feel like you've done a bit of division. This problem is the square root of 2 over the square root of 5. The rule is you must have a rational number, not a radical, a rational number in the denominator. The denominator must be a rational number. It's not. Okay. Pardon? Yes, sir. We're going to multiply this fraction by the number 1 in a really weird form. It is square root of 5 over square root of 5. Do you agree that square root of 5 over square root of 5 is 1? So I'm not changing its value, but it certainly is going to look different. The square root of 2 times the square root of 5. You can multiply any square roots. You can only add like radicals, but you can multiply any of them. So the square root of 2 times the square root of 5 gives me square root of 10. And now, the square root of 5 times the square root of 5, it is 5. This is the square root of 25, and I'd like to skip that step each time. When you multiply a square root times itself, it's going to pop out as a rational number. Square root of 5 times the square root of 5 is the square root of 25, but that is 5. At the end of the problem, you would ask yourself, can I simplify the radical? Square root of 10? No, there's no perfect square that goes into 10. Can I reduce the fraction? No, the 10's in prison, the 5's not. He can sit there and look at it, but he can't get in. Okay, so no reducing. Is that okay? This is called rationalizing the denominator. Anytime you see a radical in the denominator, you have to make sure that you work on it so that the denominator loses its radical, becomes rational. Number 25. It says to simplify, and this time it has it written as a fraction, all of it under one radical. But this can be changed to the square root of 1 over the square root of 6. It's a good idea, if you can simplify before you start the process, go ahead and do it. Can you simplify the square root of 1? What is the square root of 1? It's 1. So I don't need a radical up there. Now the square root of 6, no, there's no perfect square that goes into 6. So I'm ready to rationalize it. I'm going to multiply by the number 1. What form is it going to be in? Square root of 6 over the square root of 6. For a numerator, 1 times the square root of 6 is the square root of 6. What's the square root of 6 times the square root of 6? It is plain old rational 6. It is the square root of 36, but we won't write that. This answer, and you're really going to have to use your tool palette, because you're going to have to set up a fraction, and then you're going to have to put a radical in the numerator. Square root of 6 over 6. It might not look better to you, but the denominator is now rational, which is a rule of algebra. Let's look at 26. I'm supposed to rationalize the denominator, and I have 9 over the square root of 9x. Okay, I'm going to keep the 9. Can I simplify the square root of 9x? Isn't that the square root of 9 times the square root of x, which is rational 3 times the square root of x? You don't have to do that first, but I think it's best if you do. If you can simplify anything before you start the process, do so. All right, now, there's a radical in that denominator against the rules. What will you multiply by? All you have to do is worry about the radical, so it's square root of x over square root of x. What will that give you? What will it give you in the numerator? 9 times the square root of x. He can't go in there. That's a prison cell. What about in the denominator? It will be 3 plain old x. Because square root of x times square root of x is the square root of x squared, which is back to x. Now, can I do a little more reducing? In fact, could I have reduced it way back at, yes, do it anytime you want. I just am seeing it right now. So if I reduce, 3 goes into 3 once, and 3 goes into 9. That isn't legible. Great. Three times. Can't really read that. I'm sorry. Shouldn't have chosen that color. So it's 3 times the square root of x over x. Because I did not lose this radical. All right, I'm going to pause the recording and let you work on number 27. It asks you to rationalize the denominator, and I have 7 times the square root of 2 over the square root of 5. All right, when you worked on this, is there any radical that you can simplify before you start the problem? No, I have a square root of 2 and a square root of 5. There's nothing I can do with those. What did you multiply by? Square root of 5 over square root of 5. Now, I've not talked adequately really about multiplying radicals, but probably your instincts took over. The 7 is a rational number, so it's sitting out in front. You multiplied the square root of 2 times the square root of 5 and got the square root of 10, and it's over rational 5. Notice the difference. It doesn't have a radical anymore. Square root of 5 times square root of 5 is the square root of 25, but that is 5. Can you reduce the rational parts? No. Done. So if you got 7 times the square root of 10 over 5, you were correct. There's another kind of fraction which means it's another kind of a division problem that we need to be able to rationalize, and it's one that might contain two terms, a plus or a minus. Now, I need to pause for a minute because when I created this lesson, I omitted something. So I'm going to have to come in here and do this little practice now. All right, multiplication. We've already talked about some of this. If I have the square root of 2 times the square root of 7, I just multiply the radicals and get the square root of 14. I would always ask myself, can I simplify it? Maybe I can, maybe I can't. In this case, I can't. But what if I had the following? What if I had the rational number 3 plus the square root of 2 times 4 plus the square root of 5? And somebody asked me to multiply those. What does that remind you of? FOIL. Because it looks kind of like a binomial times a binomial. We're going to use the FOIL process. The product of the first, 3 times 4 is 12. Outer, I'm going to multiply 3 times the square root of 5, and that's exactly what I get, 3 times the square root of 5, and it's positive. Inner, I have 4 times the square root of 2, which I can't do anything with. It's 4 times the square root of 2. The last, what am I multiplying? Square root of 2 times square root of 5, which is square root of 10. Sometimes you can combine some of these terms because they might end up having like radicals. But did mine? No. And so, unfortunately, that's what I get. 12 plus 3 times the square root of 5 plus 4 times the square root of 2 plus 10 is the product. Right? Let's look at another one. What if I had 3 times the square root of 2 plus 5 times 4 square roots of 2 minus 8? Although you might not need it, I'm going to go ahead and write down everything again. The product of the first. It is 3 times the square root of 2 times 4 times the square root of 2, which gives me what? I have 3 times 4, which is 12, times, what's the square root of 2 times the square root of 2? It's 2. It's the square root of 4, which is 2. So the product of the first is 24. Anybody want to talk about that in more detail, or did that make sense? I multiplied the rational factors. 3 times 4 is 12. Square root of 2 times square root of 2 gave me the square root of 4, but that is 2. In other words, square root times itself, it pops out. And then 12 times 2 is 24. Outer product, I'm going to have 3 square roots of 2 times a negative 8. What can I multiply together in this product? The 8 and the 3. Okay, so if your instincts were telling you that, you're right. The 2 is under the radical, so it's in prison. So 3 times negative 8 gives me negative 24 times the square root of 2. Whoops. Inner product. I'm going to multiply 5 times 4 times the square root of 2. And what's that going to give me? 20 times the square root of 2. And that was all positive. And then finally, for the last, I'm going to multiply 5 times negative 8, which is negative 40. That's okay. All right, if we can see all of this up here at once, is there any of this that we can combine? I have a 24 and a negative 40. Do you agree those are both rational factors? And then I have negative 24 square roots of 2 and positive 20 square roots of 2. Doesn't really matter what order you write them. 24 minus 40 is negative 16. Negative 24 times the square root of 2, positive 20 times the square root of 2 gives me square root of 2. And that's my product. That's a huge problem because I needed to do FOIL. You might be able to do these products in your head, and that's great. But in the notes, I wanted to show everything. Let's do one more multiplication problem. It was a big oversight of mine to not get any of these in the exercises. Let's take 5 times the square root of 3 plus 7 times the square root of 2, and let's square it. Now, if you want, you can write it down twice. 5 times the square root of 3 plus 7 times the square root of 2 times 5 times the square root of 3 times 7 times the square root of 2, and do it by FOIL. Perfectly fine. So you can use FOIL or shortcut. And I'm about to use the shortcut. The shortcut is the process for squaring a binomial. Square the first. Okay, if you square that, 5 times, it's going to be 5 square root of 3 times 5 square root of 3, which will give me what? 5 times 5 is 25, and square root of 3 times square root of 3 is 3, so that's 75. Maybe you could do that in your head. To get the middle term, you need to multiply these two together. So it's 5 times the square root of 3 times 7 times the square root of 2. And what do you get? 5 times 7 is 35 times the square root of 6, but we're not done. Because to get the middle term, when you're squaring a binomial, you have to double it. So I'm going to multiply by 2, because what that represents would be both the outer and the inner product. So there's 2 of those, so there's 70 square root of 6. So you multiply and then you double. And then you square the last one. It is 7 square root of 2 times 7 square root of 2, which gives me what? 49 times 2, which is how much? 98. And this turned out to all be positive. Any of those terms alike to be combined? 75 and 98. Those are both the rational numbers. And what do I get? 173 plus 70 square root of 6. And that's exactly what you would have gotten if you did FOIL. The product of the first would have been here. 35 times the square root of 6 would have turned out to be the outer, and it would have turned out to be the inner. So that's why I doubled it. And then that would have been the last. So this is a shortcut, and if you hated it, use FOIL. You'll get the same answer. Okay, that was a little trip down multiplication lane. And we are back to 28. It asks us to rationalize a denominator, but this time there is not just a single term down there. This one is 9 over 2 minus the square root of 7. You're still going to multiply by the number 1. If you multiply by the square root of 7, that won't fix it. I could show you. Don't write this down. I'll erase it in just a second. If you use the square root of 7, which people want to use, well, you would have to distribute it. And you would get 2 times the square root of 7 minus, what's the square root of 7 times the square root of 7? It's the square root of 49, which is 7. Look at that denominator. Did you get rid of the radical? No. So that didn't do. There is something that you would not have heard of before, and it is called a conjugate. Yes. And I said you wouldn't have heard of it, but some of you have in a previous math background. The conjugate of this expression is the same two terms, a 2 and a square root of 7, but it's the opposite sign between them. I'm about to have what you might remember as a sum and difference product, but I have to have the same thing on top. So when the denominator of a fraction has a plus or minus with a radical, you multiply by the conjugate, and I will show you why. All right, first of all, if you multiply in the numerator, 9 times 2 is 18, and 9 times the square root of 7 is 9 times the square root of 7. The denominator. Think about FOIL. What's the product of the first? 2 times 2 is 4. Now, the outer product is positive 2 times the square root of 7. What's the inner product? Negative 2 times the square root of 7. And anytime you multiply conjugates together, the inners and outers cancel out, which means you don't ever have to think about them. Then what's the product of the last? What's negative square root of 7 times positive square root of 7? Well, negative times positive is negative. And what's the square root of 7 times the square root of 7? It is 7. It's the square root of 49, which is 7. That leaves me with a numerator of 18 plus 9 times the square root of 7 over negative 3. And the only way that you could reduce this is if all three rational numbers have a common factor. And they don't. Oh, yes, they do. Duh. The only way you can reduce it is if they have a common factor, and they do. So sorry. Can I divide negative 3 into those two numbers that are highlighted on top? Yes. Negative 3 goes into 18, negative 6 times. Negative 3 goes into 9, negative 3 times, and I keep the square root of 7. And that's my reduced answer. Do what? No, because the negative 3 is the coefficient of that square root, so I can't do anything more. All right. Let's look at another one where we're going to rationalize the denominator and we've got to use the conjugate. All right, number 29. Can y'all read the problem? Those of you in class? If you can, you've got really good vision. All right, I guess I can rewrite it. I have the square root of 5 minus the square root of 3 over the square root of 5 plus the square root of 3. If I'm going to make a rational number in that denominator, then I'm going to have to multiply by the conjugate. What's the conjugate of the denominator? Square root of 5 minus square root of 3. Square root of 5 minus square root of 3. Now the denominator should be the easy part. When they're conjugates, what's the product of the first? What's square root of 5 times square root of 5? 5. Outers, inners, I don't care because it's a sum and difference product. What is the product of the last? Square root of 3 times square root of 3 is square root of 9, which is 3. So the denominator is 5 minus 3, and I'll replace that with a 2 in just a minute. So you could have done FOIL, or you can recognize that it's a sum and difference product and not worry about the whole thing. Now, the numerator. I do need to use FOIL. What's the product of the first? 5. Now, the outer product is what? What is the square root of 5 times the square root of 3? Square root of 15, and it's negative. Negative square root 15. Well, what's the inner product? It's negative square root of 15, so that is negative 2 square roots of 15. And what's the product of the last? What's the negative square root of 3 times the negative square root of 3? It is positive square root of 9, which is positive 3. All right, my final answer, the numerator. I've got a 5 and I've got a 3, so that gives me 8 minus 2 times the square root of 15 over, what's the denominator? 2. Did I end up with another problem that could be reduced? Yes. What does it? 2 goes in there once, 2 goes in there 4 times, 2 goes in there once, and I'm going to get 4 minus, I'm not going to write that 1 square root of 15, and I'm not going to write over 1. It's just going to be 4 minus the square root of 15. Okay, I'm gonna stop the lesson there. We've still got some class time, but I would imagine that you're at saturation right now. So I will record this as Chapter 10, Part 1, and then tomorrow